down a bit more, about right? What's everyone's mood? I'm relaxed either way. Fine? Yep, all good. That way I can see people have any questions and all that sort of jazz. Okay, so welcome everyone for our third talk, Introduction to Astronomy for the year. I'm just seeing who's coming in here and get some handouts. Here you go, guys. Here's some handout. Have you got two there or one? One? I'll get another one there for you. Just get another one handout. Now, oh yeah, someone else just has turned up. Here's a handout for you there. Do you want to pass one back? And another one over here. Now, you'll notice on the handouts, I was just going to say, welcome to our third one of the year. You'll notice the date on the handout, 1st of March, because this one was destined for March, immediately after Jonathan's one on dark energy, but COVID lockdown sorted that, so we did an online one, so I wanted to hold this back to do it today. So here we are. Let's start going. Now, so in February, Jonathan here gave us a great talk on dark energy, and he pretty much pointed out to us, it's a little bit fuzzy, but on a large scale, this is what the universe looks like. It looks like a big sponge or a big soap sud. And you've got here these sort of light bits here. These are filaments and sheets, nodules here of galaxies and clusters of galaxies. And there's sort of like a web type. They call it the cosmic web. And like a web, you have these areas here of relatively empty space called voids. And Jonathan, you'll recall, showed us that right permeating through all of the cosmic web, there's a relatively weak force called dark energy, and it's repulsive, anti-gravity in nature, poorly understood. But the bottom line is, where you get these sort of areas here, these nodules and sheets and filaments of galaxies and galaxy clusters, the gravity from them trumps the dark energy. So it holds everything together. But in these regions here where there's very little matter in these voids, you've got this expansion going on, and that's what's driving the expansion of the universe. So leading on from there, Jonathan's talk was all about the stuff here. So tonight, I want to show you all about the stuff in here. In particular, what you see here. So Jonathan told us that 70% of the universe matter/energy is made up of this dark energy, which leaves 30%. And 30% of the universe is matter. And out of that 15% of that 30% is just these bright galaxies, what we call baryonic or normal visible matter that goes up to make you, me, these chairs, the stars, the planets, Jonathan as well. He's made of this normal baryonic matter. So, which leaves the other 85% of the 30% of matter is something you can't see here. It's called dark matter. And that's what we're going to be talking about tonight, because it naturally begs the question, what is dark matter? How do we even know it exists? And what possibly could it be? So that's why tonight's talk is, what is dark matter? The evidence, the candidates, and the search. Okay, who can tell me what's the name of this object, this astronomical object? Can anyone give me the name for it? Yeah, the bullet cluster. Well done, Andrew. It's one of my favourite astronomical objects. Love it. And can anyone tell me the significance? Why have I shown this image tonight? What's the significance of this image in the context of this talk? Come on, Jonathan.
It shows the distribution of dark matter flowing further than the baryonic matter. So
yeah, the bottom line is, it's arguably the strongest evidence for dark matter is in this image, which I will be going to later in the talk, explaining the details. Yep. It's called the bullet cluster. Well worth looking up and having a read at home. So the three sticky messages I'm going to impart to you tonight, which I'll go over at the end, but I can't help myself, and I get so excited, I just got to bring them up front for you. You're going to find out tonight that dark matter is an elusive particle making up 85% of all matter. There is compelling evidence for its existence, and it's what holds galaxies and galaxy clusters together. In fact, it's vital in the formation and the stability of galaxies and galaxy clusters. So the roadmap of how we'll go about doing it, I've broken it into 5 chapters. So first of all, we'll talk about the definition, what is dark matter, where is it distributed, and it's very important, I've got to bring in here, called the standard cosmological model, the evidence for dark matter, and I've put asterisks beside those 2 topics because that's really what I focus on tonight. And I think we will have some time where then we'll go over proposed candidates' experiments to detect dark matter and alternative theories of what possibly could be an alternative to dark matter. I've purposely done the handout sort of swung more towards that side. Now we're going to talk about the first 2 topics in more depth. And then summary, we're going to go over those 3 sticky messages again. So chapter 1, let's talk about the definition, distribution of dark matter and the standard cosmological model. So what is dark matter? Well, first of all, it's a form of matter implying stuff, particles. It's not some sort of process going on or some sort of law of physics. It's postulated. It is a particle or a matter, some stuff. I'll let you go. Okay. It does not absorb, emit, or reflect light, electromagnetic radiation. And that's why we call it dark matter. So it doesn't interact with light at all, hence the name dark. It interacts with other matter through gravity, and that's the key how we know it's there. You might say, well, how do you know it's there? Because it doesn't reflect light, it doesn't emit light, it doesn't absorb light. How do you know it's there? It's through its interaction through gravity. You think, really, how does that work? Well, a very good analogy of that is wind. Yeah, who's here seen wind? I know I haven't, but I see the effects of wind. On a winter's day, you're sitting inside, you're looking outside, you can't see the wind, but you see the trees all leaning over, you see the rubbish bin rolling down the street, so you know damn well, you look out the window, so it's a windy day today, but you can't see the wind, but you know it's there through the effects. It's the same with dark matter. You can't see it at all, but you see it through its effects, through interaction with gravity. And the other thing, yep, as I've mentioned, it makes up 85% of all matter. Now, just putting that in the context, because sometimes it can get a bit confusing, the percentages. So the universe is made up, as Jonathan said, 70% dark energy, and that 30% of matter. So you break that in, and that's 25% matter, dark matter rather, and just 5% normal matter, our baryonic matter. So that 85% is taken off the whole, that's 85% of that 30%. Okay, so where is dark matter distributed? It primarily hangs around normal matter, or you could argue the other way around, normal matter hangs around dark matter. So it forms spherical halos around galaxies and clusters, and here's a nice, just a little diagram here of the Milky Way, which is a spiral galaxy. There's this bulge, there's the disk, and there's a stellar halo around here, sort of a few old stars around here, as most of them are all the young stars in the disk. But right around that halo of stellar halo, there's a much larger halo of dark matter. We'll be talking about how do we know that shortly, but I'm just pointing out that's where the distribution is. And also, I should take a step back. So what are galaxy and galaxy clusters? Galaxies are gravitationally bound bunches, thousands, millions, sometimes billions of stars, all held together as one unit through their own gravity, holding each other together. It might be a spiral galaxy like the Milky Way, they're all going round in the central disk. It might be elliptical galaxy, sort of a more elliptical, spherical type of object. But either way, all the motion of those stars within it are all held together as a single unit through gravity, and it's called a galaxy. A galaxy cluster is pretty much the same principle, but on a bigger scale. So instead of stars forming a galaxy, you've got multiple galaxies all gravitationally bound together as one single unit in motion, but they're all connected and gravitatingly interacting with one another, keeping it together as a unit, and that's called a galaxy cluster. So same concept, just on a bigger scale. So round galaxies, you get this big spherical halo of dark matter, and the same as galaxy clusters. So here's a galaxy here. You can't see it, but there'll be a massive big halo of dark matter right around it. And here is a nice galaxy cluster, multiple galaxies. They're all gravitationally bound together in motion, and there'll be a huge big halo of dark matter around that cluster. So essentially, galaxies and clusters are embedded in dark matter halos. And the evidence is to suggest, certainly in the Milky Way, the ratio of normal matter to dark matter, 1 to 10. There's probably 10 times more dark matter to normal matter around the galaxy and the halo. It's a massive halo in which these galaxies and their clusters are embedded in. Okay, so let's talk about the standard cosmological model. And it's known as lambda cold dark matter, or abbreviated lambda CDM. What that refers to, lambda refers to the dark energy that Jonathan talked about in February, this sort of anti-gravity repulsive force that's going on in these voids responsible for the universe expanding. It's got a value which of course makes up 70% of the universe. Dark matter, which we're obviously talking about tonight. And cold. The word cold means relatively low velocities compared to the speed of light, as opposed to a hot cold matter would be dark matter particles zooming around at huge velocities close to the speed of light. Cold dark matter refers to these dark matter particles, very elusive, but they're not travelling very fast. They're nice and slow, so they use the word cold. The standard cosmological model, so that's the name of it, and it takes into account the proportions, which we've talked about, the 70% dark energy, 30% matter, which dark matter is 25% of that, of the whole lot, and normal baryonic matter that goes to make up you, me, the chairs, planets, stars, and Jonathan, makes up just 5% there. So that's the proportions. The evolution simulation, so I've written that there to refer to, so they know what the universe, they go back in time and they estimate what it would have been like in some big hot plasma when the universe formed with these proportions of dark energy, dark matter in its cold form, baryonic matter in its form and that percentage. They plug that into the computer, plus plug in all our laws of physics, how things should behave, how things should interact, run the simulation through 14 billion years, and what do you get? That exact picture, exactly what we see in the sky when you look out to the heavens today. So it's pretty strong evidence, that in itself, for dark matter, and that's why I've introduced it right up front, the standard cosmological model. Gravitational clumping, I put in there just to refer to to a concept that actually highlights how important dark matter is to us, to our very existence. As you know, matter's got to clump together through gravity for stars and galaxies to form. They've got to get something to those seeds to get that process going. As I've told you, there's a lot more dark matter in the universe than there is normal matter. And the word clumping refers to as if you get small areas of overdensity, they will just get more and more dense because of gravity. Regions of less dense material will get less and less dense as material gets contracted more and more to higher regions of higher density. And it's those initial seeds of dark matter in the early stages of the universe that was able to get that whole clumping process going, where slightly over dense areas were able to attract more dark matter, get these sort of densities going, which then normal matter can drive in on the ride and form stars, the very first stars and galaxies. So that sort of pretty much sums up the importance of dark matter in the whole universe now in our existence. So what is the evidence for dark matter? There's actually numerous forms of evidence, but there's 5 main lines of evidence which we'll go over. The velocity of galaxies and galaxy clusters, how fast stars are going round spiral galaxies, hot gas and galaxy clusters. We'll talk about gravitational lensing and our friend the bullet cluster. And then we're going to talk about the cosmic microwave background. So these are our 5 main lines of evidence that this dark matter is out there, that we can't see, but we know is there. So Yeah, high velocities of galaxies and galaxy clusters. Who can name this famous Swiss-American astronomer did all his work in the 1930s? Come on, guys. Yeah, Fritz Zwicky. Yeah, absolutely. Considered by many the father of dark matter. And I've put this picture here. It took a while to actually find a reasonable picture of the guy. He was interesting, he was eccentric, and he rubbed a lot of people up the wrong way. He was sort of quite abrasive in his approach to people. So there's a lot of not so nice photographs and images of him. But I did find a nice one. He was very ahead of his time. He was absolutely brilliant in what he did. He was decades ahead of the rest of the astronomical community. And he was the first person to postulate the existence of dark matter. So how did he do that? What he did, he started observing one of the clusters called the Coma cluster. And he picked out about 8 galaxies there, and he was able to use spectroscopy to get an idea of their velocities, their radial velocities, how far they were travelling towards us or away from us. And he concluded from there, after his calculations, and said, the galaxies and the velocity, the speed at which these galaxies are travelling within the Coma cluster is too high. It shouldn't be so. And the concept being is that if you've got these gravitationally bound units, whether it be galaxies or galaxy clusters, and you've got these galaxies zooming around, it makes sense. The thing that's holding them together is gravity from mass. And if you have something flying around too fast, where there's not enough mass or not enough gravity to hold it together, it's going to fly apart. But they weren't flying apart. So he said, look, there's something missing in here, because what he did, he worked out the velocities, the average velocity of the galaxies, totaled up all the mass of the galaxies he could see, and he said, there is not enough mass. We cannot see enough mass to account for the velocities of the galaxies without the whole cluster just falling apart, flying into pieces. There's more matter going on in here in this cluster than we can possibly see. That was the 1930s. And I think he was decades ahead of his time. No one paid much attention to it. And also because of his personality, I think a lot of people just pushed it to one side. But nevertheless, it's quietly sat there in history until really the late 60s and the early 70s. And actually, I've just put this here. Those who are technically or mathematically inclined, there is an actual formula. It's called the virial theorem. Whereby if you get a self-gravitating spherical system of objects, whether it be a galaxy or a cluster of galaxies or a globular cluster, anything like that, that's self-gravitationally holding it together, if you know the size of it, if you know the average velocity of it, there's a very simple formula, and all that's derived from the kinetic energy of something is half mv squared. And then that translated to potential energy, but it's a very easily worked out formula. So given the size and the average velocity of objects in a self-gravitating spherical system, you can calculate the total mass. And that's what's essentially what he did. He said there's just not enough visible mass to hold it together. So it's a very straightforward formula that he was using. So that took us right up to about 1970 or so to this lady who started doing some work on the rotational velocity curves of spiral galaxies, which we'll talk about now. So she's a very famous pioneer of dark matter. Can anyone tell me her name?
Vera Rubin.
Yeah, Vera Rubin. Well done, George. Yeah. So Vera Rubin. There she is there. She died, sadly passed away on Christmas Day 2016. Who else died on Christmas Day 2016? Entertainer.
George Michael.
Yeah, George Michael. I was going to say it's been forgotten already. Gosh. Okay. So sadly she passed away on Christmas Day 2016, but she was also right up there with Fritz Zwicky in terms of one of the very early pioneers, and she pretty much brought all his work back to life again. So let's have a look what she did. So she picked out a series of spiral galaxies relatively close. This one here is what they call a rotational curve for the Triangulum galaxy, which is M33, which is one of the 3 spiral galaxies in our local group of galaxies. The other one, of course, being the Andromeda galaxy. So what she did, she measured the velocity at which stars and all the gas in these spiral galaxies, the rate at which they were rotating around an orbit around the centre of their respective galaxy. And she was able to plot here velocity in kilometres per second, and she did that as a function in light years of the distance from the centre of the galaxy. So she did that for a series of galaxies, and this one's the triangulum. And the laws of physics tell you that this is the expected, because the same sort of principle, as you start getting further and further out, the velocity must drop off, because if the velocity remains out there and you don't have mass further out in the galaxy, the stuff's just going to fly off in all directions. And one of the formulas how you work out the mass inside a certain area in a spiral galaxy is you actually work out the velocity from velocities, and you can work out the mass inside that area. But what she found was completely contrary to that. Look, this was the actual observations that she made. The velocities just went up and up and up, and just then started plateauing out only when you're so far out from the centre of the galaxies. The gas and the stars in the outer part of the galaxies had rotational velocities around the galaxy centres much, much more than you would ever expect. So why don't those outer regions of gas and star, why don't they just fly off? And the reason being is, yep, there's obviously some sort of hidden mass there. I put this one here. This is a 21 spiral galaxies that she did in her study. So it wasn't just a one-off thing. You can see the trend is pretty clear there. Okay, so this implies that with these spiral galaxies, as we've sort of introduced to you early on, a few slides earlier on, that spiral galaxies are embedded in huge, big sort of clouds of dark matter, which can be up to 10 times the mass of the visible mass that go to make up a spiral galaxy. So that's the velocity of galaxies within clusters. That's the rotational velocity of stars and gas, particularly in the outer regions of spiral galaxies, because good evidence. So at this stage, the whole astronomical community sort of pricked their ears up. Oh gosh, Vicky was actually quite right. And yeah, there's no doubt about it. Something is going on out there. So with the space age and stuff, they would have a closer look at things. Who can tell me the name of this famous space telescope and what sort of class of range of wavelengths that it views in? It's my favourite telescope, Andrew. Yeah, so it's the NASA Chandra X-ray Observatory, and it observes from space X-rays. And it's proven to be vital, sort of a key instrument in gathering evidence for dark matter. Okay, so these galaxy clusters that we mentioned, they're sort of just big systems of entire galaxies, all just in motion, all sorts of motions going on there, but gravitationally held together. Another component of galaxy clusters is gas, hot gas, just between the galaxies. There's just particles just going on, zipping, zapping, because of course temperature hot is just a reflection of how fast something's moving. It's kinetic energy. So the Chandra X-ray was able to observe the hot gas in particular. What do hot things emit? Anything in motion emits electromagnetic radiation or light. And the hotter you get it, the higher the wavelength. And it detected all these X-ray emissions coming from these galaxy clusters. And the X-ray emission was referring to temperatures of up to sort of 10 to 100 million degrees Kelvin of hot gas particles, all making up the galaxy cluster between the actual galaxies. And obviously that indicates huge velocities. And once again, if the only mass in galaxy clusters was just the galaxies that you can see, this gas would not be able to be so hot. It would have either had to be a lot cooler, or if it was that hot, it just would have flown off. There's unseen gravity within galaxy clusters that must be there. We can't see it, but some form of mass must be there to keep those hot, highly energetic, high velocity gases contained within their respective clusters. So our fourth line of evidence is through gravitational lensing. Gravitational lensing is the natural phenomenon first predicted by Einstein's general theory of relativity, whereby anything of mass distorts the fabric of space-time around it. And of course, the bigger the mass, such a galaxy or galaxy cluster, really distorts to a significant degree the space-time around it. Furthermore, if you manage, so say if this is Earth here, if you can get a nice alignment of Earth with some massive object, like a galaxy cluster, or large galaxy, and lying here, that's warping and bending space-time around it. That's in line with another object, a further distant object. The light from that distant object comes out, it heads out this way, gets bent and twisted back towards Earth like that, and we see images out of here. Even though it's sitting here, we see the images of it out here. So the bottom line is the resultant of the gravitational lensing effect is that of a faraway object, we're able to see magnified, multiple, distorted images of that distant object through this whole process of gravitational lensing, space-time. So here is an image. In the foreground here, you've got a galaxy cluster. And you notice all around the edges of all these sort of multiple distorted sort of images. And what you're looking at here, is the images of distant galaxies behind this cluster. And the key here is not only does this whole image and this whole process of stuff going on, does it give you magnified images of distant objects, you can do the other way. You can also work out from there, analyse and deduce what you've actually got in front of you, how much mass and where that mass is distributed. If you're finding you get more distortion in a certain pattern, that tells you you've got X amount of mass, in particular in a certain part of that so-called gravitational lens. So the nature and the amount of distortion and magnification is analysed to determine the amount and distribution of the closer object's mass. And that's the important part coming up here with dark matter. So here it is, the famous bullet cluster. And what you're looking at here is you've got two galaxy clusters. Remember, a galaxy cluster is a big gravitationally bound collection of galaxies all cruising around, and loads of hot gas, hot baryonic, normal matter gas. And you've got another one here, nice gravitationally bound, of galaxies and hot baryonic, normal matter in gas form zipping around really, really hot. And just like galaxies merge, we've spoken about before, the Milky Way, it's going to merge in about another 5 billion years' time with the Andromeda galaxy. They'll still be talking about Penlink. And Winston Peters will still be in some form of politics. They're going to merge. Galaxy clusters are no different. Just everything's a galaxy cluster is very similar to a galaxy, but just on a much grander scale. So we're dealing with galaxies, not individual stars. But what you're looking at here, two galaxy clusters have actually, not in the process of merging, they've actually have merged, and they've come out the other side of each other. And what we've got here is, I'm losing my pointer, but that's all right. So you can see here these galaxies are all in place. These are the galaxies of the galaxy cluster that was once over here. These galaxies sitting here are the galaxies of the galaxy cluster that was once over here. So the galaxies, like stars, when galaxies merge, the distance between individual stars is so great. They very rarely actually collide. It's the gas that gets together and rock and rolls and merges and has all sorts of crazy reactions. The stars themselves don't. Same principle with galaxy clusters. When clusters merge, the space between galaxies themselves is so large, the galaxies quite happily sail through each other. So you've got the galaxies here that have gone completely through. The pink refers to is an X-ray emission. It's been colour-coded pink, and that's taken from the Chandra telescope of hot X-ray emissions from the hot gas. So when the gases of the two clusters met, they do clash, because of course gases are closely, the atoms, individual atoms are relatively close together. So you get that hot reaction, you get a lot of emission. And what else do you know is that bullet sort of shape, there's bow shapes there, bow shapes. Obviously they've collided, there's resistance to them going through and reactions. So that's from what you'd expect from hot baryonic, hot gases colliding and creating that reaction. Now, the other thing you see on this picture here is, notice the distortion all around the outsides of that. There's obviously gravitational lensing going on. And they looked, and they analysed all the degree and the amount and the distribution of the distortion around that image. And from then, they could infer the distribution and the amount of matter that was going in here. So they worked out the amount of matter that should be there, deducted what you can see in visible galaxies and deduce the amount of dark matter was there. And there's two significant things in this picture that really drive home the evidence for dark matter. One is, look how much both clusters are totally in that big embedded, in that huge big ball of dark matter. And the other thing you notice, just like the galaxies, they haven't interacted, they've just quietly gone through each other. So you know there's matter there, you know there's matter that does not interact with baryonic matter. It must be some sort of exotic particle, non-normal, non-baryonic. It's not interacting with any other material. You only know its presence by gravity. And it's this image here of, you can see the dark matter halos quietly moved through. It's gone completely through, unimpeded. It's there at large quantities. How do they know? Through gravitational lensing. And that's why that image is probably arguably the strongest evidence there is that dark matter, these exotic particles, do exist. Okay, so the fifth line of evidence is the cosmic microwave background. And you might wonder, what on earth is that? You've probably heard of it. The bottom line is the universe is filled. We're bathing in it right now. It's everywhere. These sort of low energy microwave wavelengths of radiation right through. And it equates to a temperature of about 2.7 degrees Kelvin, which is pretty cold, and that's the temperature of cold, deep space. And I put the picture of the TV there. Why have I put a picture of an old-fashioned TV there, an old analog TV? For my heading for cosmic microwave background. Because remember the old TVs and you change between channels where it's all crackly and you'd see all that big fuzz? A good deal of all that crackle and fuzz and interference and noise between your TV channels and those old TVs was your cosmic microwave background. You're actually seeing the background cosmos. What were you listening to and looking at? It's pretty much the very first light emitted by the universe when it was only 380,000 years old. That's what you've been listening and watching. What'd you do? You probably changed the channel to I Dream of Jeannie or something like that and got on with something more productive. Okay, so let's talk a little bit about it. Just a bit of background here. In the first 380,000 years of the universe, it was very hot, it was very crowded, such that your charged particles, namely your protons and your electrons, and your photons were just zipping around. They just were so energetically, by joining to something else, was just booted off again. So it was all just one big, hot, mixed up soup of charged particles, protons, electrons, and photons, all going crazy. In other words, the universe was opaque to light. Slowly the universe expanded and cooled until it got to roughly about 380,000 years old, whereby it had cooled sufficiently enough for suddenly the protons and the electrons were allowed to combine and stay combined together. So you formed your first neutral atoms, and that in turn allowed suddenly the photons of light, instead of just ricocheting and bouncing off charged particles, absorbed, re-emitted and so on, suddenly were free to travel throughout the universe unimpeded. Initially, they were probably at temperatures where it was in the visual wavelengths, this first light that formed. But of course, so they immediately just pervaded or permeated right throughout the entire universe, was just filled with all these photons. But what happened to the universe? It's continued to expand further out and cool down. And those photons, those original photons, are frozen in that time, and as the universe expanded, those photons have got stretched and stretched and stretched to longer wavelengths, and they are now in the microwave wavelengths, which equates to about 2.7 degrees. And they're all around us right now. We are bathing in them. We can't feel them because it's really, really low energy microwave, but you can see them in your old TV sets. So that's what that is known as the cosmic microwave background. So it's cosmic because it's right throughout the entire universe, and it's in the microwave wavelengths, and it forms the background of which the rest of the whole universe is all built up from. So how do we know it's also whether it's there, and what can we do about it? Well, there's been there's been various balloons and all sorts over the years, but there's been three major satellites produced by NASA and the European Space Agency, the COBE and WMAP from NASA and the Europeans put up Planck, each one successively more and more advanced, and it's being able to map out, record and map out the cosmic microwave in detail. So what do you get? You get something that looks like this, and it looks like a big jumble, doesn't it? Each of those little speckles, or blotches if you will, what they represent is really, really tiny, 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 fine little fluctuations in temperature. You know, we're talking 1 part in 100,000, tiniest of little fluctuations. But the instruments, particularly the Planck one, was sufficient to detect these little wee fluctuations and bring them out. These little fine temperature fluctuations in the cosmic microwave background in turn reflected fine little density variations of matter. Remember I talked about that importance of the concept of clumping, in particular dark matter, which is far more abundant than normal matter, and where you get slight little tiny little increased density, a region of increased density, just through gravity. It suddenly attracts more and more material around it, so the dense regions get more dense, the less dense regions get less dense. It's called clumping, so matter just through gravity tends to clump itself together. And what these little specks represent, tiny temperature fluctuations due to tiny little fluctuations in matter. We're going to a talk on the cosmic microwave background, probably in about 2 or 3 months' time or so, and we'll go into a much, much more depth. We'll pull that whole diagram apart. We'll rip it apart and have a hell of a lot of fun with it. So we'll have a ball with it. So that's what we're going to do in 2 or 3 months' time. So that's just a bit of an introduction to it. So what do you do with that? Yeah, there is a wealth of information in there, a wealth. So what do you do? How do you get that information out? Some clever guys, they came up with the idea of constructing a histogram chart known as the angular power spectrum of the cosmic microwave background. And what they did here, they plotted the temperature of each of those tiny little blotches. And they squared it, and these are in micro-Kelvin degrees, so a millionth of a Kelvin degree, and then you square it. So they put that up at the x, on the y part of the chart. Along the x line, there's a function of the angular size in the sky of those specks. So, for example, if we go back, for example, you might say these bright ones here have a 1 degree. If you look up in the sky, it's about a 1 degree angular size, and the other specks are a lot smaller, and so on. So they totaled up, analysed all the zillions of specks that are going individual specks, and were able to plot them of the temperature versus the angular size in the sky. And what you get, see these little red dots? This is the data, the lines of data that they got there. It sort of tails off, 2 nice humps here, big spike here at 1 angular size of 1 degree, and then you see here, this region here, a little bit increased error. So you might say, well, what's the green line going on there? The green line is, remember I talked about the Lambda cold dark matter model, where they get their big supercomputers out, they shovel in loads of dark energy, loads of dark matter, just exact proportions as we think our models are right, what models are based on. You throw in all your laws of physics, the way things interact and stuff. Remember, I told you run your computer for 14 billion years rather, and you get that cosmic web. But equally, if you run your computers through into the cosmic microwave background, what would it look like now? That green line, that's from the model analysis, the computer model analysis of the cosmic microwave background. It just perfectly matches the exact of what you actually observe in the sky today. And what is an integral part of that cosmological model? Dark matter, cold dark matter, making up 25% of the energy matter substance of the universe. So if that's not a damn good argument for, if I haven't convinced you now, I'm not going to. That's not hard evidence that the cold dark matter is there. Just a little bit of just whetting your appetite, which will go when we do analyse the cosmic microwave background. Look at all the other information that's in there. These peaks all represent things here. The top peak represents the total energy in matter. Normal matter is represented by this peak, and these series of smaller peaks down the sides, it represents the total dark matter. And that totals up to 25%. Furthermore, just another little thing that backs this whole model up involving the cosmic microwave background, which, as I've illustrated, involves 25% of everything being cold dark matter. It's a long story. Through a process called baryonic acoustic isolations, which we'll talk about in a couple of months' time, you get these sort of speckled pattern, and from there they're able to analyse or run the computers forward, and with all the laws of physics and everything in place for our model, and you should get this statistical circular distribution of galaxies. And what do they find when they're doing all the statistical and spatial arrangements of galaxies today? What do they see? They're seeing these exact statistical spatial arrangements of galaxies and galaxy clusters exactly as predicted if you got the patterns of the cosmic microwave background and shoved it through the Lambda cold dark matter model. Once again, it's just the evidence is well and truly everything's fitting for it. So, just in summary of our 5 key lines of evidence, you've got the high velocities of galaxies within galaxy clusters. Why aren't these clusters just flying off in all directions? There must be more matter than we can see holding it together. Likewise with spiral galaxies, you get these stars and gas further way out in the spiral galaxies. That stuff is just whipping around at velocities that if there wasn't something holding it together like hidden mass, it'd just be flying apart. The hot gases, up to sort of 10 to 100 million degrees of these gas particles flying around between galaxies and the galaxy clusters. If there's some other mass out there, otherwise that gas would be flying off. The gravitational lensing effect, you're starting to get this gravitational lensing, you're looking at these distant objects and from then reducing how much matter is actually in front to create that distortion of space-time to allow for that distortion, and it's showing that you need a lot more mass in those up-front objects than you actually see in the clusters and the galaxies. And then we've looked at the very first light that shone from the universe when it was 380,000 years old, to what we see now, and the patterns just fit beautifully with the cosmological models allowing for 25% cold dark matter. So let's move on to chapter 3, proposed candidates for dark matter, and what sort of experiments, so what are they doing about it to actually find out these particles, to identify them and to exist. The first step you've got to do is let's have a look at the apparent properties. If you're going to go looking for them, you've got to know what you're looking for. So we'll look at the apparent properties of these dark matter particles. Then we'll look at there's loads of candidates, but there's 3 key candidates. And then we'll look at the experiments designed to try and detect these particles. So what are the properties of dark matter? Well, dark, that's the obvious one. We know it does not interact via light, electromagnetic radiation. It neither emits it, it doesn't absorb it, it doesn't reflect it, you can't see it, but it does interact through gravity with other material. We know it's abundant. Our calculations tell us it can be up to 10 times the visible mass of a galaxy or a galaxy cluster. You total up the mass you can see, and we know there's much more, up to 10 times more matter than that actually there we just can't see. So it's very abundant, and it must be very stable, because it certainly doesn't decay, it's still very much there. It's very widespread. I'll put this up here just to remind us that it's sort of pretty much, as we've talked about, all the stars and galaxy clusters that I've spoken about are embedded in these much bigger sort of clouds or beds of dark matter. So one way of looking at it is that your visible light from your stars and your galaxies and your clusters, they only make a small proportion, but they're your traces. They're outlining where the dark matter is. So that's a good way of looking at it. And we know from the cosmic web that Jonathan showed us in February, the cosmic web is right across like that on large scales across the universe. So we know that dark matter is widespread. It's pretty much everywhere. We also know, we've talked about, it's cold. For it to form that gravitational clumping, to start bringing it together to create clumps and clouds of it, which then allowed the first normal matter to do the same through gravity, get attracted to those bigger clumps, more powerful clumps of dark matter, it must be moving at relatively slow speeds. Any particle dark matter proposed candidate that's flying around at high velocities would not have, it would be too high for it to go through clumping. We know it goes through clumping, and particularly in the early universe, to fit the models of the Lambda cold dark matter. So we know it's cold. In other words, it's not rapidly moving particles. They're just cruising along at sensible speeds. Okay, so what sort of candidates could there be? So we're looking at candidates for particles, subatomic elementary particles that we haven't seen yet. So we've currently got the standard particle model, which is a model of all the basic elementary particles that we're aware of. And that model works so well, it's brilliant. But we know it's incomplete. We know there are holes in it. There's a lot more work to be done on it. And there's various sort of particle physicists are busy working on extensions of that standard particle model. And they're proposing a range of hypothetical elementary particles. And the two big groups are called weakly interactive massive particles, in other words, WIMPs. In other words, weakly interacting, in other words, they're not strong, but they do interact, namely with gravity, and they've got some sort of mass to them. They're not massless. So they've made it this nice little increment called WIMPs. And then the other group is called axions. So let's have a brief look at these. So these WIMPs are massive. They're larger than protons, so they're a decent size, these hypothesized particles. The two big ones is called neutralinos, and they are particles as sort of a spin-off, if you will. There's all sorts of theories out there, M theory and so on, but there's one called supersymmetry theory, which is well beyond the scope of this talk. But that has particles called neutralinos that would fit the bill quite nicely for cold dark matter. Then there's another form of particles called Kaluza-Klein particles, and he's named after two particle physicists who were working on this whole area way back in the 1920s. And they were putting forward a theory of the universal extra dimension theory that is being put together, and these particles are part of that theory. So there's two possible candidates. And the other one is axions, which are smaller than WIMPs, smaller than electrons, and they from the Paki-Quinn symmetry theory, once again beyond the focus of this talk, but it's to do with violation of charge parity, violations involving gluons and quarks, the strong nuclear force. There are violations there that you should and shouldn't see. There's a problem going on there, and two famous particle physicists, Paki and the other one was Helen Quinn, developed this sort of symmetry theory that would solve that sort of problem going on with particle physics. And the particles that they described to fit in with their theory, they're called axions. And I just threw this at just a little bit of a quirky sort of little story. They were named, how do you name all these particles? And it was named after a brand of a dishwashing liquid in the US. That's how they got named axions. So little anecdotal, quirky story there. Okay, so what are they going to do? How are we going to find these particles? We know they're elusive. We know they're pretty small as well. We're going to have a hard time looking for them, but we know they're also really, really important to understanding the universe. You know, they make up, 25% of the entire substance of the universe. So they're very important. But yep, it's challenging, it's expensive. No one sort of institute can possibly take on a project like this. So it's usually international collaborations. There's different ways you can do it. In particular, referring to this whole scene is through direct observing, trying to find the particles. You can also try to find them indirectly, which we'll talk about it, and we'll talk a little bit about what you can do with particle accelerators. So these big detectors, there's 14 worldwide so far that they've got. They dig them deep underground. Why? Is to reduce noise. What they're trying to do is they get these huge big tanks full of cryogenics or and stable noble gases like xenon, argon and so on. They fill them in these big tanks and they sit there waiting for one of these proposed particles in case one comes along, really might strike one of these noble gas nuclei, and the nuclei would recoil and you'd get some energy given off. And it's lined with multiple detectors and amplifiers trying to detect, possibly, please happen. One of these rare events might happen. The deep underground to stop noise, because possible noise, cosmic rays. In other words, little charged particles zooming across the universe, at high energy. Where are they coming from? Probably from supernova explosions. And they just travel unimpeded through the universe. They would make mincemeat of this and quite happily fly through there. So you've got to bury it underground to try and cull out a lot of the cosmic rays. The water shields around it is to stop natural radioactivity and radioactive decay going on with rocks underneath the ground. And so they put water shields around to protect them from that. And then they just sit there and wait for one of these rare collisions with maybe a WIMP might quietly cruise through there and have reactions. Sadly and frustratingly, they've had no results to date. People argue that WIMPs are dead in the water. I don't know about that. Then the axions, and the detection of axions is based around the principle that these hypothesized particles, according to the theory, that if they go through a very strong magnetic field, they will get converted to microwave photons. So the idea is to try and set up your magnetic field, hope that an axion, if they exist, travels through your magnetic field and converts and gives off a microwave photon. The problem is with that is these photons are really, really going to be faint, and they don't know quite what frequency they're going to be at yet. So there's been experiments that have all come up with negative results, but that's helping them constrain it down to maybe, if it is there, what sort of range of wavelengths they may be. So this is the first one here in the University of Washington. There are new detectors coming online. So a lot of people are putting their money on the search for axions. There's sort of a lot of people who argue that that's the future of dark matter searching. How about indirectly? So you know that matter and antimatter is out there and it collides or it self-annihilates itself and creates gamma rays? Well, dark matter in theory should do exactly the same. If you've got dark matter particles out there, you'll have dark matter antiparticles are out there. And yep, they will meet and they'll collide and they'll give off gamma rays. So off a particular calculated wavelength. So the Fermi Large Area Telescope, which is designed to pick up gamma rays, they point that towards the centre and also the disk of the Milky Way, whether they're hoping to sort of perhaps a higher density of dark matter particles, and they're seeing if they can pick up tiny little flashes of gamma rays that would be consistent with dark matter and dark antimatter self-annihilating itself. Sadly, no results to date. In a similar principle, that whole process, not only would it give off gamma rays, it's theorised they would give out high-speed, high-velocity neutrino particles, subatomic particles, which, yes, you can have neutrino detectors. There's two main neutrino detectors aimed, or in particular partially designed to look for the neutrinos they would expect with the properties that they would expect from this dark matter, dark antimatter colliding together and self-annihilating. One is, I believe, in the sub-Mediterranean ocean off the shores of France. But the other one, sort of, that's quite spectacular, is this ice cube one that's based in Antarctica. And they've got a cubic kilometre here, where they're digging down big holes that go up down to about 2.5 kilometres. There's 86 of them there with strings going the whole way down, between 1.5 to 2.5 kilometres down, each with 60 sensors on it, trying to pick up signs of neutrinos, these subatomic ghostly particles that could also can just quietly just zoom through the Earth. So that's something there. Once again, no results to date. Well, if you can't find them, make them. And that's what the Large Hadron Collider they're trying to do underground in Switzerland, getting the energy levels up to see if they can produce these elusive dark matter particles. So I believe it's going through a bit of an upgrade at the moment, and they hopefully might be able to do this in the future if these dark matter particles exist. But of course, after tonight, you know they exist. So how about what other... There's always people out there with other alternative theories, or possibly what it could be, despite good, hard evidence. So let's have a look at the two most common ones that you'll hear. One, massive compact halo objects, or the acronym MACHOs, and of course that's a play on words against the WIMPs, MACHOs versus WIMPs, and MOND, which stands for Modified Newtonian Dynamics. So the idea behind MACHOs is that the theory is that maybe out there in each galaxy and stuff, there's a whole big stack of large mass, not necessarily large, but just sheer numbers, but there's mass there from objects that we just can't see very well. They emit small amounts of light or none at all. Black holes, neutron stars, brown dwarfs and so on. There's people who postulate that these really dimly lit objects are out there, probably up there in enough mass to account for dark matter. And how they would try and pick them up is through gravitational lensing. Here would be your macho, for example, a brown dwarf star, and you'd see the light of a distant star behind it being distorted in a particular characteristic way, indicating you've got a mass in front here. So they do use this method. They can pick up these faint objects within the Milky Way, but the bottom line is there's just not enough mass that they've detected through this to account for the mass that's clearly there holding galaxies together. So that sort of is just an idea that's getting thrown around and probably left there. How about MOND? So there's one group of physicists who came up with the idea that maybe in areas of low acceleration, that the laws of physics perhaps are a little bit different, that Newtonian laws are a bit different. And we're all familiar with Newton's law that says that force between objects is the mass times the acceleration. Well, they're proposing in these areas that way out in these looking at these rotational velocity curves, way out in the sort of outer suburbs of spiral galaxies, that maybe the formula is different, that it's mass times acceleration squared. And the force between objects, instead of, as you know, Newtonian physics says it's the inverse square of the distance between objects, they're saying that maybe that the gravitational force between two objects is actually just purely the inverse when you get to these outer areas of low acceleration. And the good news for these guys is, yep, that model fits perfectly well for rotational galaxies, for spiral galaxies, rotational curves and spiral galaxies. But sadly, it does not match up with doesn't explain the whole scene in the cosmic microwave background. It cannot explain the hot gases and clusters, and it doesn't come anywhere near, it hasn't got a hope of explaining what you see in that very famous a bullet cluster image. So it's got more than its fair share of problems. So a lot of people say that's dead in the water too. I've certainly never been a fan of it, but anyway, I've told you about it. So, summary. Really, these three sticky messages. So dark matter, it's an elusive particle that makes up 85% of all matter. There's compelling evidence for its existence. And it's what holds galaxies and galaxy clusters together. In fact, it's vital for the formation of stars and galaxies to form them and to stabilise them. So I hope you've enjoyed What is Dark Matter, the evidence, the candidates and the search. Thank you for your attention. I hope you haven't been as bored as this character. Anyway, any questions around that? Yes, John.
Completely irrelevant comment, but from a biological mental viewpoint, it looks remarkably like a neural network.
It does look like a neural network. It certainly does, yeah. It does. That cosmic web looks like a neural with the little nodes and the little filaments going off. It looks just like you see neurons in the brain and the spinal cord. Looks exactly like that. Absolutely. Yeah. Woo, dark matter. Yeah. Any other questions? I hope you got all your handouts there. I've got a couple of copies if you want more information of the full paper here, but I've pretty much designed it whereby I sort of top heavy near the end, but that I went over a little bit quicker. But
You've got any copies of extra information, have you?
Yeah, you want one?
Yes, please. Light to be interested.
There you go. It's just for you.
Could you in future include a photo of your friend on the last page and stand down?
Oh, my friend here. Yeah. Oh, lovely. It's Toby. Yeah.
For spiral disk galaxies, how do you know that the dark matter is in a halo and not just in a disk shape like the regular matter?
Yeah, because mapping it out, the visual, they're able to map it out. Yeah. Sorry,
From the gravitational lensing?
Yes, various methods they can do that, and it seems that the galaxy is just embedded in a big cloud. It's a spherical halo. It is spherical. And there's numerous ways, mainly through looking at other galaxies, to be honest, is how you look at it, the gravitational lensing. and so on. You can work out the amount of mass and the distribution of it. And it's in spherical halos around your spirals and your elliptical galaxies, and likewise around your galaxy clusters. Big spherical halos, which it's easier to think of just to pick up a galaxy just embedded in this giant cloud. And it's quite a cool way when you look at the cosmic web. You think, where's the dark matter? Well, just think of the stars and what you can see. It just traces for where the dark matter is. They're following the dark matter. Yep.
Does the halo go further than the Oort cloud?
The Oort cloud refers to the solar system, which is just a tiny, tiny, tiny part of our galaxy. But the whole galaxy is permeated through dark matter. But the Oort cloud, like our galaxy is just our solar system. The Oort cloud is what, about a light year out, isn't it? As opposed to the Milky Way is about 100,000 light years. So it's, yeah. But in answer to your question, it just goes right throughout the whole galaxy. Does that answer your question?
So the dark matter doesn't get concentrated around solar systems in any way, shape, or form? It's
Probably little
uniformly
subtle.
across the galaxy, is what you're saying?
I've led to believe, because I remember asking a cosmologist that exact question. It was down the Dunedin now, or who was the guy from Sydney? Joss. Asked him that exact question, and he says there is a slight shadow, looking for a better word, a slight increase now, like the bulge of the Milky Way has slightly increased concentrations. So the galaxies are embedded in these big clouds of dark matter, but also there is a little bit more of it around, like the bulge of a spiral galaxy and so on. And hence the Fermi LAT telescope, they're pointing it towards the bulge, the centre of the Milky Way, because there is, in answer to your question, yes, there is slightly more amounts of dark matter where you see normal matter. Does that?
It's really just at big scales.
Yeah, on big scales, as opposed to your clouds, a relatively small scale. But yeah, yep, I think we're all good.
Are there any future scopes going out that might help these theories? Like to replace the Chandra scope?
Chandra's still going.
It's still going?
Yeah, oh yeah, it's still going. And the XM Newton stuff. There's the two of them, and the European one, the XM Newton, both of them were launched in 1999 and still going strong. But there have been, there's been about a dozen or so modern, newer generations gone up, but those babies are still up there working, those old two stalwart workhorses. But yeah, there's loads and more sophisticated X-ray telescopes up there as well that have been launched in the last 20 years. Yep. So it's a very exciting field of astronomy. Are we all home time? Yep, and I think next time we're going to talk about, in a month's time, special relativity. Remember last year we did general relativity and gravity? And then Jonathan and I will put our heads together and work out something for the cosmic microwave background. We'll have fun with that. So, okay, everyone, safe driving home and have fun. Happy Easter. Thank you.